Hello again. I'm sorry that I lost the end of this tape last time. My machine didn't have enough room to go for more than 10 minutes, but I have taken care of that so I can keep going. I was told I ended on the three-way handshake, so I'm going to start there and make sure we understand that. The main point that I was making was about the finite state machine. Again, this is a theoretical concept of computer science which is used in many, many applications. Operating systems, networks, all over the place. And you will get it in a very formal setup in the algorithm, in the computer theory course that we're now going to have, we're now required, and it was offered for the first time last semester. It's not an awfully hard concept. What you have is you have three sets. You have a set of states. So we presume the algorithm, the protocol, is in a particular state at any one time. It's just a way of saying, what are we waiting for? What are we doing? What did we just do? Whatever. Then we have a set of events. These are things that can happen. For example, in the transport TCP, a timer can go off that says we waited too long for something to happen. Also, another event could be that we received an acknowledgement of a message we sent. The events can come from outside where, the protocol, in which they're called exogenous events, or they can come from inside, such as the timer, and those are called endogenous events, but you don't need to know that. Now, there's one more set involved in the finite state machine, and that's the concept of actions, what we can do. Actions for the TCP would be send a message, resend a message, set the timer, turn off the timer. So again, those are the three we have. Now, I think I mentioned this before. The way that protocols are created is a committee or a group of people work on it. And then when they like what they have, they publish it. They publish it in what's called a request for comment, an RFC. And then the whole world can look at it and decide whether they like it or don't like it, or what they think is ambiguous, or ask any kind of questions about it. Each of them is numbered, and the lower the number, the longer ago it was created. I think they're up in the thousands, 800, maybe 8,000, something like that. This one is 793 for the TCP. It is 40 years old. It's been modified some, but the original was 40 years old. Now, I'm going to show you the picture they have of a finite state machine. One of the ways we represent it is by basically a graph showing the states as nodes and the actions as transitions from one node to another. Watch out. You're not going to think much of this graphics, believe me. Remember, it's 40 years old. There's the graphics. Now, what this has at the top here is the setup for a TCP connection. Before we can start sending information, we have to synchronize the two sides. What that means is we have to decide on what sequence numbers we're going to use. I'm going to start at 1, so the other side expects a 1. I send him or her 2048 bytes. he acknowledges that he got 2048 bytes and is expecting 2049 is the next one. And I put the sequence number 2049 on what I send to him. That way we know if we lost something and things are out of order. So the sequence numbers are very, very important. And the way things happen is one side sends the sequence number, the other side acknowledges it. You're going to find out very shortly that both sides send things and receive things. So there's really two sets of sequence ACK numbers, one for the sender and one for the sender on the other side. We start off here, let's say in the listen state. So that's a state. Now in that state, the TCP is waiting. And it's probably waiting, it's waiting someplace. It's at a socket. It gets a message. It gets a sync from someone who wants to use it, wants to get it to transport something to it, or wants to set up a back and forth communication. Once it receives that sync, you can see receive, sync, then it goes into a new state, sync received. When you looked at the Wireshark, sync and ACK were 1-bit flags in the headers of the messages that were sent. So when we say we receive a sync, we get a message with sync flag set to 1. Now, we sit here waiting. We need a response. We get it. Pardon me. We receive the sync. Now, we have to send something. We send back a sync ACK. That means we set both the sync flag and the ACK flag and send it back to the person who talked to us first. That person then, at that point, the TCP goes into a state called sync received. It waits. It expects to get back an ACK of what it sent. If it receives the ACK, it doesn't take any action. It just says, I'm established, we're ready, we can start communicating back and forth. So that's the three-way handshake. I send a sync, the TCP sends a sync ACK, and I send a sync back, an ACK back, and we're set up. Now the rest of this is how to close it and things like that. I'm not going to worry about that at the moment. And you can look a little bit more at these if you want to. As I said, an FSM, a finite state machine, has 3 sets of elements and a function. But don't get too excited about these fancy words. The first set is just a set of states. It's the protocol is always sitting in some state. All a state means is what it's waiting for. What is it doing? You could be idle. You could be listening to TV, whatever state you happen to be in at that moment. The second state is the set of events. These are the things you're waiting for. Every time one of these events happens, then you're going to react to it. So I'm waiting for some kind of event. The third set are the things I can do. Now in the TCP, I can send a packet. I can resend a packet. I can set a timer. I can turn off a timer. I can send an acknowledgement. All these things are possible actions that I can take. So we have 3 sets of items. The states we're in, the events that will push us to do something, and the actions that we'll do because of the state and the events. The function says, I give you a state and an event. And if that function gets the state and the event, then it's going to tell you what state you should go into next and what action you should take. So if I'm sitting here and I'm listening and I get a sync, then I'm supposed to go into the sync receive state, and I'm supposed to take the action of sending a sync ACK to the other side. So you could formalize that, but I think it's enough to just realize that. Now, why is this good? You could write a program very easily from this. What you're looking at is a justification for a case statement or a big if, else if, else if, else if, else if, whatever. All you're really doing is saying, if I'm in state A and event B happens, then change state to X and execute this function. And you have thousands, you can go on and on and on for every state and every event. So it's almost an automatic writing. It's just a big, big statement. Now, the TCP, you have to remember, fits between the application and network layers. What this means is that the application layer, maybe email, maybe a request for HTTP, it sends a request down to the TCP. So the client, the email client may say, send a message, get my email. Now, the transport layer looks at that, puts a header on it, and then it sends it to the transport layer on whoever is the server, wherever the server is. As far as the transport layer is concerned, the item is going from the source to the destination. But that's not true. The TCP, the transport layer, is actually taking the message it got, putting the header on, and passing it down to the internet layer. The network layer. And the network layer is in charge of getting it over to the other side now. The transport layer just says where it has to go. The network layer has to figure out how to get it there. What intermediate steps nodes it's going to go through. So there are really four actions that the TCP, at least four actions we have to think about that go with the interfacing between the layers. Because besides the direct connections we're thinking about between the layers, between the transport and the transport, we have to think of how we interact with the one above us and the one below us. Now, these have fancy names. ADT send P says, the application passes the data P to be sent across the network. So basically, it's taking what it was given and passes it to the internet. To the network. ADT receive says the network layer delivers a message to the transport protocol. So those two are interactions with the internet. The next two are interactions with the application. The action UDT is send the P to the network layer. Pardon me, I think I had that wrong. Well, I'm not sure that's right, but we'll see. And the deliver data says, deliver the P that I got from the down here in the network layer up to the application layer. You should just think of these as, I get something back, I get something from here and I have to send it on. I get something that's coming from the other side, I have to send it on. Now, there's another way of looking at it. Maybe an easier way for you to think about it. And that's to think of it as a table. It's really just a big table. The first column is the state, the second column is the event. This is the action we do. This is the next state we have. Ack means acknowledgement. Knack means negative acknowledgement. I didn't get it. It wasn't right. And what I'm showing here is basically what the TCP above is going to do. It's waiting for the first message. It's just sitting there and saying, I'm idle, let's see what happens. It receives the message. It receives the data. It makes up a packet, sends the packet to the network layer, and it goes to this data waiting to get a response back. So now it's in the wait for ACK packet 0. Oh, by the way, it also sets a timer. A timer is just a counter. It counts down to 0. And when it hits 0, it goes off, sets an alarm. Maybe through an interrupt. Somehow it says it causes an event. So we're waiting for the ACK packet 0. Well, the best thing could happen, we received it. If we receive it, turn off the timer and wait for the second message to send. Because it got there okay, we don't have to worry about it. Now we receive a packet with a NAC of 0. It didn't get there. So we have to resend it with the sequence number 0. The checksum is just a way of looking at all the bits and trying to create a number. And the other side does the same calculation. And if the two numbers are the same, then we have some belief that the message wasn't tampered with on the way. It's not perfect, but checksums are used. We'll see those later in the semester. Now, if we receive the NAC, we have resend it, we go right back to the same state. We're still waiting. Well, the third thing that can happen is the timer goes off. Well, what should we do? Resend it. After all, it didn't get there yet, so we better send it. And again, we're still waiting for the ACK or the NAC. Now, once we get that ACK or NAC, we can wait for the second message. And all these steps are going to be done again. So I didn't bother putting them in here. But basically, they're going to be the same. Now, think of how you would write this as a program. You'd basically set a state. Then you'd have an infinite loop. And the loop would wait for one of the events to happen. It would be outside the program. When you put input data in, that's outside the program. So you're waiting. If the first thing you get is send the data, then you immediately do this and you change the state. If it's something else, you may just ignore it, go wait for the first message still. But you can write the program from this information. This is called event-driven programming. And it's a reasonable way to program. Now, this is a bad protocol. It only sends 2 messages at one time. It's only a communication in one direction. It's so bad that if you use this, it takes a very large, good bandwidth and brings it down to almost nothing. Now, how do we show what's happening? We set up a picture of how things are going. Time is going to run down the page. This is called RDT 3.0 in the textbook. And we're going to keep building on it and make it better. The first one is I'm in dreamland, I'm in utopia. Everything's perfect. Well, in that case, the sender sends packet 0. It arrives at the receiver sends back the ACK, and that arrives at the sender sends packet 1, and we just keep going and going. And everything is beautiful. Now, however, suppose we send packet 0, and somehow we receive packet 0 back, and we send packet 1, and packet 1 disappears into the ether. Well, we time out. That's the event that happens, and we resend packet 1. Anything could happen in between. That space that's empty in between the sender and receiver is the hostile territory we're sending this stuff through. Now, the ACK could get lost. That might mean the receiver gets the same packet twice. I didn't draw that, but that could happen. The ACK is sent, but the receiver does not get it. There are all kinds of things that could happen. Now, this shows you how bad it is. Essentially, if we have a 10 to the 9th bits per second, that's a huge one. That's 1 followed by 9 zeros. We bring it down to 33 followed by 3 zeros. That's not good. And that's what we're going to be improving on as we keep looking at better and better algorithms. Now, that's where I'm going to stop now. What I'm hoping to do is send you a little bit of homework on this. It'll be on finite state machines. It won't come directly from the text. I'll probably make it up. I have some of it written, but I want to make sure it's not going to be impossible. So we'll see what we can do. I expect you'll get it tomorrow. So good luck now, and keep at it. So long.